Ever feel like you're staring down a mountain of information, knowing you need to understand it inside and out? Like you're gearing up for a major exam where every detail could be crucial.
Yeah, that feeling is pretty familiar.
That's exactly the feeling we tackle head on here at the Deep Dive. Our goal is to equip you with a thorough understanding of complex topics, cutting through the noise to deliver the essential knowledge you need to truly master the subject.
And today, that major exam we're tackling together focuses on control logic design within computer organization and architecture. You, our listener, provided us with COA M4 and we're treating this as our comprehensive study guide. Our mission is to meticulously break down the core concepts. We want to ensure that by the end of this, you feel completely prepared, ready to explain how a computer's control unit operates at its heart.
Exactly. We're not just doing a quick review, we're going deep to build a solid foundation. We'll explore what control logic design is, the various ways it can be structured, and the critical differences between hardwired and microprogrammed control.
Right.
Think of this as your intensive study session. By the time we're done, these core principles should be crystal clear. So to kick things off and really lay the groundwork, what exactly is control logic design?
In essence, control logic design is the process of creating the digital circuits that dictate how a computer system functions.
Yeah.
As our source material explains, digital systems store information in binary form within registers.
Okay.
This information can be the data being processed or, and this is key for our topic, control information that governs the system's operations. Control logic design is about building the circuits responsible for both manipulating this data and generating the control signals that orchestrate these manipulations.
So if we're thinking about our exam, we need to understand that control logic design is fundamental to both the data processing and the overall management of a computer system. It's kind of like the conductor of an orchestra, right? Making sure all the instruments play in harmony.
That's a perfect analogy. And keeping everything synchronized in these digital systems is the job of a master clock generator. This clock emits regular pulses that time the activity of all the registers, including those within the control unit itself.
The metronome for the orchestra.
Exactly. Think of it as the metronome keeping the beat.
The document also mentions timing diagrams and flowcharts. How are these helpful in understanding control logic design, especially when we're trying to really, grasp the concepts?
These are invaluable tools for visualizing the abstract world of control signals and algorithms. Timing diagrams allow you to see exactly when different control signals are active relative to each other over time. It's like a musical score showing when each instrument plays. Flowcharts, on the other hand, map out the step-by-step sequence of operations, the algorithm that the control logic needs to execute. They help you understand the logical flow, including any decision points, much like a recipe outlining the steps in a dish.
Okay, so if we're studying for our exam, we should think of timing diagrams as showing the when, the temporal relationships and flowcharts as outlining the what and how, the logical steps of the algorithms. It's about understanding both sides of the control process.
Precisely.
And it seems like this design of the control logic isn't an isolated process. It's connected to other things.
Absolutely not isolated. The source emphasizes a critical point. Control logic design is deeply interwoven with the development of the very algorithms the system needs to perform and the specific architecture of the data processor that the control logic is directing.
Okay.
You can't effectively design one without a clear understanding of the others. They are all, interconnected pieces of the puzzle.
Right. That makes sense. It's a holistic approach. So once you've figured out the sequence of control operations needed for a particular task, let's say, executing an instruction, how do you actually build the system to make that happen? That's where the section on control organization in our study guide comes in, I guess.
Exactly. Once you've established the desired sequence of control operations, you need a sequential system to implement them. Now, you could, in theory, use standard sequential logic design procedures. However, the document highlights some significant drawbacks of taking that direct route for complex control tasks.
Okay, for our exam, we should really understand these drawbacks. What are the potential problems with just using standard sequential logic for control design?
Well, for anything beyond very simple control sequences, you can quickly end up with a huge number of distinct states that the control logic needs to manage.
Right.
This explosion of states leads to a need for a large number of flip-flops to represent these states, and a corresponding increase in the complexity of the logic gates required to manage the transitions between them.
Okay, that sounds complicated.
And furthermore, the traditional design methods that rely on state tables and excitation tables become incredibly cumbersome and, frankly, difficult to manage in practice when dealing with a large number of states. Imagine trying to fill out a state table with hundreds of rows and columns. It becomes a logistical nightmare.
Yeah, I can see that. That paints a clear picture. So for our exam, the key takeaway is that while standard sequential logic could be used, it quickly becomes impractical for complex control due to the sheer number of components and the difficulty of the design process itself.
Correct.
So what's the overall goal then when we're thinking about effective control logic design? What are we aiming for?
The ultimate goal is to create a circuit that implements the required control sequence in a way that is both logically sound and relatively straightforward to design, understand, and maintain. To achieve this, designers often employ methods that build upon the foundations of classical sequential logic, but incorporate more structured approaches, like register transfer techniques.
Register transfer.
Yeah, these techniques focus on how data moves between the registers within the system and how the control signals orchestrate these movements. It's a higher level view.
Okay. And our study guide then lays out 4 primary methods for organizing this control. Let's start with the first one, which sounds quite intuitive. The one flip-flop per state method. What's the fundamental principle behind this approach? For our exam, we need to be able to explain this clearly.
The name really says it all, doesn't it? In this method, for every unique state that your control sequential circuit needs to go through, you dedicate a single flip-flop.
One state, one flip-flop. Simple enough.
Right. Now, here's the crucial part to remember for our exam. At any given moment, only one of these flip-flops will be in a set state, typically representing a binary 1, while all the other flip-flops in the circuit will be in a cleared state, representing a binary 0.
So it's like a single token, maybe? A token that moves from one flip-flop to the next, and each flip-flop represents a distinct stage in the control sequence. That sounds like a very direct mapping between the states and the hardware.
Exactly. Think of it as a single control bit that propagates sequentially from one flip-flop to the next. This movement is governed by the decision logic within the circuit, which determines which flip-flop should be set next based on the current state and any relevant conditions. Each flip-flop, when it receives and stores this control bit, signifies that the control unit is in a specific state and should perform the corresponding actions.
The source provides an example of a 12-state circuit. If we were using the one flip-flop per state method, how many flip-flops would we need? This seems like a good test question.
Precisely 12 flip-flops, one for each of the 12 distinct states. Now, the document also points out that if you were to use more efficient binary encoding methods, you would only need a minimum of 4 flip-flops.
Only 4. Why 4?
Because 4 flip-flops can represent 2 to the power of 4 or 16 unique states, which is more than enough to cover the 12 states of our example. 3 flip-flops would only give you 2 to the power of 3, which is 8 states, not enough.
All right, 23 is 8, 24 is 16. Got it. So for our exam, the big takeaway is that the one flip-flop per state method isn't about minimizing the number of components like flip-flops. In fact, it often requires more flip-flops than other methods.
That's correct.
So what's the main advantage then? Why would you choose this approach?
The primary advantage, according to our source material, is the simplicity of the design process. Often, you can derive the control logic almost directly just by inspecting the state diagram, that visual representation of the control states and transitions.
So it's intuitive.
Very intuitive. It's a very direct mapping from the conceptual state diagram to the actual hardware implementation.
That sounds like it could save a significant amount of time and effort in the initial design phase. Are there any other benefits we should note for our exam?
Yes, this design simplicity often translates into operational simplicity too. The resulting circuit can be easier to understand, troubleshoot, and maintain. And in some cases, this method can lead to a reduction in the complexity of the combinational logic circuits needed.
But as with most things in engineering, there's likely a trade-off. What's the main disadvantage we should remember for our exam?
The main drawback is the increased cost of the system. Because you're using a larger number of flip-flops compared to more encoded methods, the hardware cost of the control unit will generally be higher. Flip-flops aren't free.
Good point. Now, the source also briefly discusses what happens if there are no external inputs influencing the sequencing when using this method. How does it behave then? This seems like a good detail for the exam.
In the absence of external inputs that can change the flow of control, the circuit essentially simplifies down to a shift register. A single 1-bit or control bit just keeps shifting from one flip-flop to the next with each clock pulse.
Okay, just shifting along.
And if this sequence of states needs to repeat continuously, the circuit becomes what's known as a ring counter.
A ring count. Okay, for our exam, we should recall that this is a specific type of shift register where the output of the very last flip-flop is connected back to the input of the very first one, creating a closed loop. So the single 1-bit just keeps circulating.
Exactly. Around and around the ring of flip-flops. And that's why the one flip-flop per state method, when operating in a repeating sequence without external influence, is sometimes called a ring counter controller. Simple and direct for repeating sequences.
Okay, that gives us a good grasp of the first method prioritizes simplicity over component count. Let's move on to the second method in our study guide, the sequence register and decoder method. How does this approach differ fundamentally? For the exam, we need the core contrast.
This method takes a different approach to representing the control state. Instead of one flip-flop per state, it uses a register, which is just a group of flip-flops working together to hold a binary code representing the current state.
A binary code. Okay.
Then it uses a decoder circuit to translate this binary code from the register into a set of individual output lines. Each output line corresponds to a specific control state.
So for our exam, we should note that this uses binary encoding, potentially more efficient for flip-flops, but then needs that decoder to get back to individual state signals. If you have LIN flip-flops in the sequence register, how many states can you represent, and how many output lines will the decoder have? This seems key.
Good question. Within flip-flops, the sequence register can represent 2 to the power of different binary codes, and therefore 5 distinct states. Consequently, the decoder will have 2 output lines, each uniquely corresponding to one of those possible states.
Right.
The example in our source of a 4-bit register is a good one to remember. A 4-bit register can store 16 different binary values, 24, representing 16 states. It would require a 4 to 16 decoder, which has 16 separate output lines.
Okay, so potentially fewer flip-flops than method 1, but we had a decoder. For our exam, how does the system move from one state to the next using this method? How does the sequence register know the next code?
The transition to the next state in the sequence register is determined by the current state of the register and any external input conditions that might influence the control flow. Based on these factors, combinational logic circuits connected to the inputs of the sequence register determine what the next binary value stored in the register will be on the next clock cycle.
So logic calculates the next state code.
Precisely. This change in the register's content effectively moves the control unit to the next state in the sequence.
And what happens if there are no external inputs affecting the state transitions here? How does it progress then for our exam?
In the absence of external inputs that would cause a jump or conditional transition, the sequence register simply advances through its binary states in a predetermined order, essentially functioning as a counter.
Ah, like counting 0, 0, 1, 10, 11.
Exactly. In this specific scenario, the method is often referred to as the counter decoder method, because you have a counter generating a sequence of binary state codes and a decoder translating those counter values into individual control signals.
All right, that makes the distinction clear. So method 1, simple, one flip-flop per state, maybe costly. Method 2, sequence register and decoder, fewer flip-flops potentially, uses encoding, adds a decoder. Our next method in the study guide is PLA control. For someone prepping for our exam, what exactly is a PLA and how is it used here?
Okay, PLA stands for Programmable Logic Array.
Yeah.
For our exam, the key thing to remember is that it's an integrated circuit, a chip, containing a structured arrangement of AND gates followed by OR gates.
And ANDs, then ORs, got it.
And the crucial part is that the connections between these gates can be programmed after manufacturing to implement complex combinational logic functions.
Yeah.
In the context of control, a PLA can be programmed to generate both the control signals for microoperations and the information determining the next state.
The source mentions an external sequence register used with PLA control. How do they interact?
In that setup, a register outside the PLA holds the current control state. This current state code, along with external inputs, goes into the PLA. Based on its programming, the PLA's outputs then determine 2 things. 1, which microoperations to activate now, and 2, what the next state code should be. That next state code is then loaded into the external register.
And the guide also says the sequence register can be inside the PLA sometimes. How does that change things for our exam?
Yes, some more advanced PLAs include flip-flops right on the chip, along with the programmable logic gates. This allows the entire sequential control circuit to be implemented within the PLA itself. The next state logic generated by the AND/OR array feeds back internally to these flip-flops, making it a more self-contained unit.
Interesting. So for the exam, PLA is a programmable way for control signals and state transitions, usable with external or internal state registers. Now, method 4 sounds really different. Microprogram control. What's the fundamental concept here we absolutely need for the exam?
Microprogram control is a completely different paradigm. Instead of hardwired logic circuits, this method involves storing the control variables, which our source calls control words, in a dedicated memory unit. This is called the control memory.
Storing control info in memory.
Exactly. Each individual control word stored there is a microinstruction. A sequence of these microinstructions for a specific task forms a microprogram.
So for the exam, the critical idea is control logic isn't wiring, it's a program stored in special memory.
That's the core insight. And because the control sequences for a computer's instruction set are usually fixed, this control memory is most often implemented using read-only memory, or ROM. The microprogram generally doesn't change during normal operation.
Okay, ROM makes sense for fixed instructions. For our exam, how does the control unit actually use this microprogram in ROM? Walk us through it.
Sure. The control unit fetches microinstructions from the control memory one by one. The content of each microinstruction, the control word at a specific address in ROM, directly dictates which microoperations should be initiated in the system at that step.
Like following a detailed recipe.
A very detailed recipe, yes. Step by tiny step.
The document mentions static and dynamic microprogramming. Key distinction for our exam.
Static microprogramming uses ROM. The microprogram is fixed. Dynamic microprogramming allows the microprogram to be loaded into a special memory, often called writable control memory, or WCM, maybe when the system starts up.
Writable, so you can change it.
Well, the source note's WCM is mainly for reading after it's loaded,
Okay.
but it offers flexibility. You could potentially load different microprograms. So static is fixed ROM, dynamic uses initially writable memory for more flexibility.
Okay, static fixed, dynamic potentially changeable. Got it. How does the control unit know which microinstruction to fetch from control memory?
That's the job of the control memory address register. For the exam, remember this register holds the memory address of the next microinstruction to be read. The ROM acts like a lookup. Give it an address, it gives you the microinstruction stored there.
And once that microinstruction is retrieved, where does it go and what happens? Another crucial exam step.
It's typically transferred into a microinstruction register. This register holds it temporarily. Its contents then do two main things. First, generate the control signals for the actual microoperations.
Okay, makes things happen.
And second, the microinstruction often contains information about where to find the next microinstruction in the sequence.
So it points to the next step. For our exam, each microinstruction specifies the what microops and often the where next address info. After the current microops finish, how is that next address actually determined?
The control unit has a mechanism. It might be simple, just increment the current address to go sequentially. Or it could be an address elsewhere in control memory, maybe based on a branch instruction in the current microinstruction, or perhaps based on external conditions or status flags.
And the next address generator circuit mentioned in the guide for our exam, that's the specific part doing this calculation.
Precisely. This circuit takes inputs like the current microinstruction, maybe with a branch address, status bits, etc., calculates the address of the next microinstruction, and loads that address into the control address register. Then the whole fetch execute cycle for microinstructions repeats.
Okay, microprogram control seems very systematic, almost like software controlling the hardware at a very low level. Now, our study guide also digs into hardwired control. For our exam, how does this contrast with the microprogrammed method we just covered?
Hardwired control is fundamentally different. Instead of storing control instructions in memory, hardwired control uses the physical wiring and interconnection of logic elements, gates, flip-flops, etc., to implement the state transitions and generate control signals directly.
So for the exam, the key difference, the logic is literally wired in, not stored in a program.
Exactly. You can think of the control hardware as a complex state machine. It transitions from state to state based on inputs like the current instruction, condition codes, external signals. The outputs of this state machine are the control signals. The sequence is fixed by how the logic elements are connected.
Our study guide outlines 5 steps for designing hardwired control. For our exam, we should probably know these. What are they?
Right. The process usually goes: 1, state the problem clearly what operations are needed. 2, define the hardware configuration. 3, formulate the algorithm the control unit needs to execute. 4, specify the data processor it will control in detail. And 5, finally, design the actual control logic circuits based on all that.
The source uses a specific example, adding and subtracting sign magnitude numbers. For our exam, can you highlight how hardwired design approaches this?
Sure. The problem: control logic for sign magnitude add subtract, handling overflow. The hardware assumed includes registers A and B for magnitudes, flip-flops A's and B's for signs, an ALU, and an overflow flip-flop E. Stack it, add QS, subtract, output X. Done.
And the algorithm. How's that derived in this hardwired example? Seems critical for the exam.
It starts with the rules for sign magnitude math. The source notes that by cleverly changing the sign of the number being subtracted and then always adding, you reduce 8 initial cases down to 4 core ones. A detailed flowchart would map out the steps for each case, comparing signs, comparing magnitudes, doing the math, setting the result sign and overflow.
So for the exam, the algorithm handles all sign combos and overflow. What about specifying the data processor interacting with this hardwired control? Key components and control signals in the example.
Figure A in the source shows this. The ALU needs selection inputs, S2, S1, S0 SIN, for its operation. A key control signal is it loads the ALU output into register A and the carry out into the overflow flip-flop E. Other signals like Y, Z, W are for complementing B, complementing A, and clearing E, respectively. These are the levers the hardwired logic pulls.
And then the control block diagram, figure B, takes inputs and generates these signals. For the exam, understand the inputs/outputs of this control block.
Exactly. Figure B shows the control logic unit: inputs, CO, QS, and 3 status signals from the data processor, like comparison results. Outputs, the X done signal, and crucially, the specific control signals for the ALU, S2, etc., and registers is the YV generated in the correct sequence. The source also mentions variable S as XORBs to easily check if signs are the same or different.
The document then mentions a control state diagram. How does this relate to the algorithm flowchart, especially for our exam?
The state diagram graphically shows the control logic's sequential behavior. Think of each function box in the flowchart, a microoperation, as a state in the diagram. Decision boxes in the flowchart become the conditions governing transitions between states in the diagram. Flowchart is algorithm logic. State diagram is the hardware sequence implementing it.
And when designing the hardwired logic from this state diagram, the source suggests using the 1 flip-flop per state method to manage complexity. Why is that method helpful here for our exam?
Well, like we said, traditional sequential design with state tables gets really messy for complex control with many states and inputs. The 1 flip-flop per state method offers a more direct, often simpler way to translate the state diagram into hardware.
How does it simplify things practically? We need that for the exam.
Because you have 1 flip-flop per state, and if using D flip-flops, the next state just depends on the D input. The source explains you can derive the Boolean logic for each D input directly from the state diagram by looking at what conditions cause a transition into that state. If multiple paths lead to a state, you just OR the conditions together.
They give an example with flip-flop T2. Remind us how its D input, DT2 logic, is derived. Good illustration for the exam.
Yes, the example says T2 should be set, DT21 if T1 is currently set, T11, or if T0 is set, DT01, and the add signal CO is active. That directly translates to the Boolean function DT2 is equal to 0 plus T1.
Okay.
It also mentions the initial state, T0 set, and that only 1 D input is 1 at any time, ensuring clean transitions.
So it's more visual, less algebraic to get from diagram to logic. Okay, let's shift back to microprogram control for more detail, especially why it's preferred for complex systems for our exam.
Right. As the source emphasizes, when you have a large instruction set with many instructions and lots of control signals, hardwired control complexity just explodes. Designing, debugging, and especially changing it becomes incredibly hard. Microprogram control is much more structured and manageable then.
Because the control logic is basically software, it's easier to change, right? Big advantage for the exam.
Exactly. Control functions are defined by the microprogram and control memory. The design is more organized, less error-prone than complex wiring, and the flexibility is huge. Find a bug, want to add instructions. Often you just update the microprogram in ROM, no hardware changes needed.
That adaptability is a major win. For our exam, what are the key components of a microprogrammed control unit again?
The essentials are the control memory, CM holding the microprograms, the control address register holding the next microinstructions address, the microinstruction register holding the current microinstruction, generating signals and next address info, and the microprogram sequencer, which figures out the sequence and loads the control address register.
Our study guide has an example sequence for add R3, R1. What does this show about microprogrammed control at a detailed level for our exam?
That example shows how one machine instruction breaks down into a series of simple micro-operations. Each micro-op corresponds to a microinstruction. For add R3, R1, the sequence might involve fetching the operand, using R3's address, adding it to R1, storing the result in R1. Each line in that microprogram, like peek out, marry, and read, activates specific control signals simultaneously.
And as we touched on for our exam, each microinstruction specifies the micro-ops and usually points to the next microinstruction.
Precisely. That next address info allows sequential flow, but also conditional branching based on results during execution.
Now, the guide discusses techniques of grouping of control signals, horizontal and vertical organization. For our exam, what's the fundamental difference?
The difference is how control signals are represented in the microinstruction word. Horizontal. Each bit position often directly corresponds to one control signal. Bit 1 means signal active, allows high parallelism, many signals active at once, but leads to very long microinstructions, maybe inefficient use of bits if many are 0.
Wide instructions, lots happening at once, and vertical. How's that different for the exam?
Vertical uses smaller groups of bits, a code, to represent an action or a set of mutually exclusive signals. This code needs decoding to activate the actual signals. Results in much shorter microinstructions, better encoding, but usually limits parallelism. You specify fewer encode actions per cycle, and the decoding step can add a small delay.
So for the exam, horizontal is wide, direct control, high parallelism, maybe less bit efficient. Vertical is narrow, encoded, less parallelism, needs decoding, maybe slower, but uses bits better. The source compares them. Key trade-offs for the exam.
Right, the table highlights. Horizontal means long format, high parallelism, little encoding, good for speed. Vertical means short format, limited parallelism, lots of encoding, maybe slower due to decoding and sequential ops.
Makes sense. It's a design choice based on needs. Now, the microprogram sequencer sounds critical. Primary function for our exam.
It's basically the control unit for the control memory. Its main job is managing the sequence of microinstruction fetches. It determines the next microinstruction address to ensure the microprogram runs correctly. Key design factors are microinstruction size and how fast the sequencer can generate that next address.
For our exam, what are its typical capabilities for deciding the next address? How does it choose where to go?
A sequencer needs several ways. It needs to increment the current address, go sequentially. It needs to branch to an address specified in the microinstruction, unconditionally or conditionally based on status flags. It needs to branch based on external conditions. It needs to get a starting address from an external source, like when a new machine instruction starts. And it needs to support subroutine calls and returns within the microprogram.
The document shows a block diagram. For our exam, main functional blocks in a sequencer.
Typically, a multiplexer selects the next address from several sources. The incremented current address, a branch address for the microinstruction, an address based on status bits, or an external address. The MUX output goes to the control address register, CAR. For subroutines, there's often a stack to save return addresses. Control logic uses bits from the microinstruction and status inputs to tell the MUX which address source to pick.
Finally, our study guide mentions microprogrammed CPU organization. For our exam, how does this control unit fit into the whole CPU?
In a microprogrammed CPU, you generally have two main parts. The data processor, registers, ALU, data pads, doing the actual work, and the control section, which is the microprogrammed control unit. The sequencer manages microinstruction flow from control memory, generating signals for the data processor. The whole CPU also needs main memory and an address processor.
And for our exam, briefly, how does fetching and executing a machine instruction work in this type of CPU?
When a machine instruction is fetched into the instruction register, its opcode undergoes code transformation or mapping. This converts the opcode into the starting address of its corresponding microprogram in control memory, often done via a ROM or PLA. The sequencer then starts fetching and executing the microinstructions from that starting address. Each microinstruction triggers micro-ops in the data processor to carry out the machine instruction.
So for the exam, the microprogram acts like an interpreter for the machine instruction, breaking it down.
Exactly. Each machine instruction has its own microprogram routine. The control unit orchestrates it all. The source also mentions using a multiplexer for conditional branching status bits and maybe a pipeline register between fetching and executing microinstructions to speed things up.
Wow, this has been an incredibly detailed deep dive into control logic design, exactly what we needed to feel prepped for that exam. To bring it all together, can we quickly summarize the most important concepts from our study session?
Certainly. We started with the foundation, what control logic is. Then we looked at 4 ways to organize it. The simple one flip-flop per state, the encoded sequence register and decoder, the flexible TLA control, and the very different microprogram control.
Right.
And crucially, we contrasted hardwired control logic built into the wires with microprogram control logic stored as a program. We hit the trade-offs for each: flexibility, speed, complexity.
And just like deep understanding is key for an exam, this detailed look gives a solid foundation for understanding how computer systems are fundamentally controlled.
Precisely.
Yeah.
Which leads to a good question for our listener to chew on. Given those trade-offs, speed versus flexibility, essentially, where might you expect to see hardwired control really preferred? And where would microprogram control be the obvious choice?
Good question.
And maybe think about how future advances, especially in memory tech, might blur the lines between these two approaches. Could they merge somehow?
Excellent points to ponder, extending our study session. We definitely encourage everyone to revisit their sources with this fresh perspective, or maybe dig even deeper into computer architecture. This deep dive set a strong foundation, but there's always more to explore.